Hey everybody, and welcome to today's lecture. So for Power Electronics, Humber College, what we're going to be looking at today is boost and buck converters. So a little bit about boost and buck converters before we get started. So what are they? So we know that in AC, we have things known as transformers. And we have step down, and we have step up. The job of transformer is to take an AC voltage value and either step it down to something smaller or to step it up to something larger. Transformers work in the AC realm. They don't work at all in DC. So if we were looking at being able to change the value of a DC voltage either up or down, we're going to be looking at boost and buck converters. So boost and buck converters, they work in the DC realm. Boost converters take the DC voltage and put it up. Buck converters take the DC voltage and drop it down. So at any time when we're looking at being able to change the value of a DC voltage, an example, you have a 9-volt battery but you actually need 18 volts of DC power. What you want to do is you want to use a boost converter. They are very efficient at what they do, and they do it very, very well. If you wanted to take a 9-volt DC battery and drop it down to 5 volts, we all know that you could run that through a voltage divider. So you just take your 9 volts and you run it through a couple of resistors, and out here you would get your 5 volts. Problem with this system is that the power or current is always flowing through this resistor here and this resistor here. So you're always dissipating heat off of these resistors to drop your 9 volts down to 5 volts. So that's a waste of energy, and something that we can do much more efficiently with something called a buck converter. So the first one we're going to do is we're going to take a look at the boost converter and see how it works. So a boost converter works on a concept of, if you remember from a while ago we did superposition theory. So back in your Tech 101 class, you looked at superposition theory. What superposition theory does is it looks at what happens to a voltage when you have more than one supply in a circuit. So we looked at it in the DC realm. So if we did something like this, we took 5 volts and a 10 volt supply. So we have the positive and the positive. If we looked at what voltage would be across this resistor here, that would be the addition of, we'll say V1 and V2, so V1 plus V2. So therefore V across the resistor. So if we looked at what's V across the resistor, in this particular case it would work out to be 15 volts. So that's pretty simple. Now the boost converter works on the same concept. So what we're doing is we are introducing a secondary supply. So if we wanted to, let's say this was our battery and we wanted a larger voltage, what we would need to do is supply another battery to the circuit so that we would actually get an increase in voltage. But that kind of defeats the purpose. You could just as easily go and buy a 15-volt battery. Why would you do two? So a boost converter eliminates that problem of you having to purchase another battery. So what we do in this particular case, you've got one battery supply, so that would be your main battery supply in the circuit. What we need to do is we need to somehow fake this one so that you end up with a voltage that's larger than what you're looking for. So we need to fake that voltage somehow in the circuit. So the way we do it is we take the circuit, we have our main power supply, whatever it happens to be, and then we know that we have certain devices that will store electricity, and one of them is the inductor. So we have our total supply, whatever you want to call it, and then we have an inductor. So the inductor actually is the component that we're using to fake that supply. So what we're going to be doing is we are going to be using this inductor, and we're going to be charging that inductor up and then using its value to boost the voltage that's already present. So here's how the circuit works. What we need is some kind of a switch down here. So when this switch, we'll call it S1, when this switch closes, let me just grab another color here. Let's hope this pen works. When this switch closes, current will flow through the circuit like so. So when current flows through the circuit like so, it actually charges up the inductor. So the way inductors work, if you remember from your previous courses, the way an inductor works is it stores its energy in a magnetic field. So when the current is actually flowing through the inductor, what we have right now is the inductor is going to charge up in this direction. So the magnetic field that is surrounding this inductor is going to be developed and the voltage that causes it is this voltage charging in that direction. So when current is flowing through the inductor and the magnetic field is building up, now we know that the magnetic field does not build instantaneous. It takes time to actually build up the magnetic field. So what happens is as the magnetic field is building and the charge is happening and the energy is being stored in the magnetic field, eventually what's going to happen is we are going to open up this switch. So a certain time or a certain point along the cycle, we're going to open up that switch. And what's going to happen is the magnetic field that is on this inductor will start to collapse. So now as the magnetic field collapses, what ends up happening is that the polarity of the voltage changes from positive to negative to positive and negative. So what happens now is we get a very large spike in energy coming from that inductor as the magnetic field collapses. So if we go back to just a couple of seconds ago, and I bring this circuit back in, you'll notice that we have a supply and a supply. Positive, positive. Okay, those supplies are in the same direction, so they're going to add up. So what we're doing here is now, as the magnetic field is collapsing, that voltage there changes direction. We now have positive and positive going in the same direction. These two supplies are going to add. So you've got this voltage, whatever it was to start with, plus you've got this spike of voltage, and they're going to go somewhere. So this switch is now open, so that voltage and current cannot go this way. So what we do is we take it and direct it this way. Now, over here is our load. So our load is sitting over here. What we want to do is we want to have somehow the voltage of this and this making it to the load. So what we're going to do is we need to be able to store this energy so that we can constantly supply the load. So when this switch closes again and we're re-energizing that coil, we need a point where the energy can be stored somewhere so that it can then feed the load continuously. So our big storage value is a nice capacitor. So the capacitor itself is a decent storage device. And what happens is, if we can get this voltage and this voltage together, it will charge up the capacitor. What value the capacitor charges up to is dependent on this value and dependent on this spike and how much energy is stored into here and how really the duty cycle of this switch, how often are we topping this up. So what happens is this voltage and this voltage combine in together and they flow this way into the capacitor. The problem with this all is that when this switch closes, you will notice that we have a short circuit. We want the current that is stored inside the capacitor, we want that current to be fed into the resistor. We don't want it to be short-circuited. So what we need to do is we need to be able to protect against the current going this way. So what we do is we take a diode and we place a nice diode here. And the job of this diode is to be able to stop the current from going back this way under our short circuit condition. So the energy from here and here can pass through the diode this way because it's forward biased. So we have a forward biased diode. Energy can pass through it, charge up the capacitor. Then when this switch closes again, and we are starting to rebuild up our magnetic field in the inductor, the capacitor continues to feed the load. When the switch opens again, the spike happens, this voltage and this voltage add up one more time, end up going through the diode, topping up the capacitor and feeding the load any extra current it requires. So basically, this and this, when the switch is open, will dump current this way and top up the capacitor. You can also assume that some current will be going down through the load. When the switch closes, the current is back into this green loop here, building up the magnetic field. Once it builds up the magnetic field, the switch will then open and dump its current. The current will then charge up the capacitor again, and it will dump some current onto the load. When this switch closes and the charging cycle happens again, and we're building up the energy inside our magnetic field, we don't want the resistor to be deprived of energy while it's doing that. So where does it get its current from? It gets it from what has been stored inside the capacitor. So inside the capacitor, we're actually taking the current from that, and it's going to be dumped into the resistor during the charge time of our inductor. So now you have to open and close this quite quickly to keep charging and dumping and charging and dumping and charging and dumping so that the capacitor doesn't get drained over time. You need to keep topping up the capacitor to its full value, or at least as close as you can, so that the capacitor itself has enough energy to keep feeding our load. So this is how the DC boost converter works. So the DC boost converter, when we are looking at our lab, this is lab number 9. We're looking at the DC boost converter. When we're looking at lab number 9, this is the circuit we're going to be building. So you'll notice that both circuits are identical except for one thing. In the first circuit that we drew, which is this one, there's a manual switch here for explanation purposes. In the lab, we've got a MOSFET. So that's a MOSFET switch. This is our resistor to protect the gate. And then we are taking a square wave from our function generator, and we are going to be taking that square wave and we're going to be turning on and off this particular MOSFET at a certain frequency with a certain duty cycle. So what we're going to be doing is taking this signal, turning this on and off. So what it's going to be doing is it's going to be opening and closing this switch, that switch. We're going to be taking that switch. Again, when the switch is closed, the electricity is going to flow this way, charge up our inductor, so our 27 millihenry inductor. So we're going to charge up the inductor. When the switch opens, the energy from here and the spike that we get from the inductor are both dumped through the diode and topping up our capacitor, or charging up the capacitor. When this closes again for our charging cycle, we can't deprive the load from getting its electricity. So what we do is it takes it from the cap. Okay, so we end up with that same topping up and supply, and then when this thing is being on, or a short circuit from here to here, and we're charging this stuff up, what's happening is the electricity is coming from the cap, so keeping the load the same. So in this particular circuit, what we've got is a boost of DC value at the output, which is our load. In the lab with this circuit, what you're going to be asked to do is you're going to be asked to adjust the duty cycle of that waveform. So when we adjust the duty cycle of the waveform, what it's actually doing is it is adjusting the amount of time that we are charging this compared to the amount of time where we are discharging this. So we all know nothing happens instantaneously. The inductor needs time to charge. It needs time to discharge. So as the charging and discharging times change because of our duty cycle, and if you remember, duty cycle on a periodic waveform, duty cycle is time on over the period. So duty cycle is time on over the period, and then you take it multiplied by 100%. So in this particular case, we would have a large duty cycle, so therefore the charge time of that inductor is larger than the discharge time. So what we're doing is we are storing more energy. The longer the duty cycle goes, the more energy we can store inside that inductor. And therefore, when we open the switch, it has more energy and more voltage to dump into the capacitor. So the larger the duty cycle, the higher the voltage that gets dumped into the capacitor, and therefore the higher the voltage that makes it to our load. If we were to take the duty cycle and make it smaller, so we took a waveform on a duty cycle and we did something like this. Oops. There we go. Okay, so we did something like this and we decreased the duty cycle. So with a decrease in duty cycle, it's decreasing the time that this thing has to charge. So as it's decreasing the time that this thing has to charge up, less energy is actually stored. Therefore, when this opens, it has less energy to dump into the capacitor, therefore a lower value of voltage coming out. In the lab, you're going to be asked to swap the duty cycles. So you're going to be asked to find a high duty cycle, a low duty cycle, somewhere in the middle. So you're going to find what these values of voltage are based on the duty cycle. The other thing that we do in this lab is swap the inductor. So we're going to go from a 27 millihenry to a 47 millihenry inductor. We all know that it takes a certain amount of time to charge up an inductor. The larger the value of the inductor, the more time is required to charge it up. So therefore, in a given period of time, you can actually put more charge on a smaller inductor than you can on a larger inductor. If you increase the time, you can actually store more in a larger inductor. But if you are looking at our duty cycle as a fixed period of time, you'll notice that you can actually store more energy or higher levels of energy in a smaller inductor because it takes less time to build up that charge. Okay, so what you're going to be doing is building this circuit. You're going to be adjusting the duty cycle. Then you are going to be swapping the inductor and then again changing the duty cycle to see what happens when you change duty cycle and change inductors. So that is the boost converter. So this is our lab number 9, which you will be doing. So moving on. All right, so now what we're going to do is we are going to switch gears a little bit, and we are going to look at the DC buck converter. So a DC buck converter, its job is to step down a DC voltage, whereas the boost converter bumped it up. The buck converter is going to drop it down. So what we're going to do is we're going to start off with our power supply again. So there's our supply, and what we're going to have at this end, here is our load. To keep that load constant with value, we have our same capacitor, and this is the part of the circuit that changes. So when we move from a boost converter to a buck converter, this part here is what gets switched around. So if you remember a couple of minutes ago, this was our boost converter. And we take that boost converter, and what we're going to do is we're going to rearrange the same components and turn it into a buck converter. So with our buck converter, our switching device goes here. Our inductor goes here. And then we'll just complete our circuit. So the way this works is when our switch closes, current will start to flow, and will flow into the capacitor and into the load and return to our source. And we have the capacitor, the inductor, charging up again like it did before. So we had that magnetic field that was being created, and the polarity was positive to negative. When that switch opens and the magnetic field collapses and the polarity switches, we need to know where this electricity is going to go. So before, we had it in the inductor, that electricity started to flow this way. In this particular case, it does the same thing. It goes this way, tops up the capacitor if the capacitor is draining, and some of it could flow into the load if needed be. Okay, and then we've got the capacitor to supply any extra that is required at any particular time. So remember, the capacitor is our big storage value, and whatever happens that's not enough from here or here, the capacitor is what fills in the blank. Okay, so the capacitor keeps the value of voltage here relatively constant as this whole thing happens. But you'll notice that when this switch opens, there's no place for this current to go. So what we are missing is our diode. And the diode is right here. So now, when that switch opens, the magnetic field collapses and the polarity switches, the current actually has paths to go. So think of this as the source, and we are supplying this source and this source. Those two things are actually in parallel, both of them supplying the load. As the capacitor is dropping, this thing is charging it up. Everything is great because now we have this return path. Okay, so the diode in this particular case provides the return path of current to the inductor. Whereas when we look at our boost converter before, we have the exact same components: power supply, inductor, the switching device, the diode, the capacitor, and the load. Same thing sits on the buck converter, but in different locations. So we have our power supply, our switching device, the inductor, the capacitor, the load, and the diode. So now how does this actually drop the value of voltage? So remember, the voltage is supposed to drop down in a buck converter. So it's going to be less than the supply. So I'm going to take you back to a discussion that we had before when we looked at what happens when we have a duty cycle involved with a DC value. So the duty cycle, remember, is being caused by the opening and closing of this switch. So this supply here is being allowed to go and then not allowed to go. So it's actually being pulsed. So if we took a supply of voltage, we turn it on at 12 volts. The amount of voltage that would make it off to a load would be 12 volts. So let's take a circuit that looks something like this, and I say 12 volts here, and here is my load. Easy question, what is the value of voltage at the load? And the value of voltage sitting at the load is 12 volts. But what happens if we start pulsing this? So let's say we put a switch here, and we start opening and closing that switch at a particular rate or a particular duty cycle. So now we say, let's take that value of voltage, that's 12 volts, and we're going to start pulsing it. So let's say we start to pulse it. And we're going to say the same, the time on and the time off are the same, so that makes this a 50% duty cycle. So remember, duty cycle is equal to the time on over the period of a waveform. So if this was a 50% duty cycle, and we had 12 volts sitting here, so that means the 12 volts, and we're flipping this on and off at a 50% duty cycle. The equivalent voltage that would appear at the load is no longer going to be 6, but it will be 12, it will be the average of 6 volts. So we look at taking the supply, so the 12 volts, times the duty cycle, and that's what equals to the voltage that makes it to the load. So if the duty cycle was 50%, then we end up with 50% times 12, and we end up with 6 volts sitting at the load. The same thing happens in a buck converter. So we bring back our little buck converter. So the same thing happens here in the buck converter. So we've got a supply here, and we are pulsing this. Based on the duty cycle at which we pulse this, this thing will charge and discharge at a particular rate, certain amount of time to charge it, and so forth. And what ends up happening is the value of voltage that makes it charging the capacitor and makes it to the load is a fraction of what we actually put in. How much of a fraction? It depends on the value of this, and it depends on the value of this. Like we saw with the boost converter moments ago, the value of the inductor and the duty cycle at which we switch it both have an effect on what ends up coming out at the load. So where do we see this particular circuit? Well, in our particular case, lab number 10 is this circuit. So I'll be doing this lab and posting a video for it. This is a switching power supply board. So this switching power supply board, this is a regulating circuit. So a voltage regulator circuit. And we'll talk more about that when I do a specific lecture on this for next week. But when we look at this particular circuit, here is our input, here is our switching device, here is our inductor, here's our capacitor, here's our load, and here's our diode. So I bring this right back, pop it on top. Switching device, inductor, capacitor, load, diode. So this top part here, minus this little resistor voltage divider here, this circuit is actually our buck converter. So again, there's the switching device, the diode, the inductor, the capacitor, and the resistor. So, buck converter job, drop the value of a DC voltage. A boost converter's job is to bump up a value of DC voltage. So hopefully that helps, and we will see you next time. Take care, everybody.